This is AP Calculus AB, and in this video I'm going to talk about section 5.2, the mean value theorem. So really the majority of what we're going to do with the mean value theorem is going to be an exploration that I want you to complete, and then we're going to discuss the results of this and talk about specifically how the mean value theorem works. But the idea on this exploration is for you to get a graphical understanding of what exactly we're talking about when we talk about the mean value theorem. So there's going to be a lot of reference to a secant line and a tangent line when we go through this concept. So what I'm going to start with here is just the first example that's in this sheet. And there's several of these that you're going to do on your own, but I just want to show you how this works. So in this first example, it says we've got a function f of x. You can see it's a cubic function. And it says there's a value of x equals c between 3 and 7, at which the tangent to the graph is parallel to the secant line through 3 and 7. So it says draw the secant line and draw the tangent line. Well, for the secant line, what we're looking at here is essentially getting a line that goes through those 2 points. So that's my secant line. Now, what I'm looking for is a tangent line that would be parallel to this secant line in the interval 3 to 7. And you can see that if I translate that line up, it's going to be somewhere around here. I've got my secant line and my tangent line would be parallel, and that's my point of tangency. So that point of tangency is somewhere around, let's see, around 5.5. So I'm going to write that here. And it says, is the function differentiable on the interval 3 to 7? Well, in this case, I would say yes, because it's a cubic function. It's differentiable everywhere. Is the function continuous on the closed interval 3 to 7? And that would also be yes, because, again, it's a polynomial, so we know it's going to be continuous everywhere. So that's sort of the idea of what I want you to do. Now, there are a bunch more of these. So you've got 5 or 6 more of these that I want you to try to solve out. And then at the end here, we're just going to talk about what all of that means in terms of the mean value theorem. And then we'll talk about specifically what are we trying to do with this. So I want you to pause the video, and I want you to work through the rest of these exploration problems. And when you have them all done, unpause the video, and I'll go through the solutions and talk to you about what exactly all of this means. Okay, so here's question number 2. And you can see on this one, we had actually 2 lines where that were parallel to the secant line, where the slope of the tangent line is equal to the slope of the secant line. And my 2 points this time were around 2.3 and 5.7. Was the function differentiable? It's the same function as before, so yes, it's differentiable everywhere. Is it continuous on the interval 1 to 7? Yes, again. All right, number 3. So this time we have a graph that has a cusp in it. So it's a little different this time. Now notice if I try to draw in a tangent line that's parallel to the secant line in the interval 1 to 5, I can't find one, because when I'm at the point where x is equal to 1, you can see how the slope is getting steeper and steeper and steeper in the positive direction. And then when we get to x is equal to 4, the slope instantaneously switches to a negative slope. So I'm never going to hit the slope that I have for that secant line with any of my tangent lines. So is the function differentiable? In this case, it's not differentiable on the open interval 1 to 5, but it is continuous on the closed interval from 1 to 5. Okay, so same graph, this time different interval. We're looking at the interval from 1 to 4 this time. Now notice this time when I draw in the secant line, I do have a tangent line that is parallel. And that happens at about 3.3. Is the function differentiable on the interval 1 to 4? In this case, yes. Is it continuous on the closed interval 1 to 4? And the answer is also yes. Now notice with the differentiability, that the open interval really makes a difference here, because the function's not differentiable at 4, but we have that open interval sign there, the parenthesis sign, telling me that I'm not worried about what's happening at 4 in terms of differentiability. All right, so now number 5, we've got a different function again. This time we have a piecewise function that's got a jump discontinuity in it. So is the function differentiable on the interval from 5 to 7? And again, open interval, yes. Is it continuous on the closed interval from 5 to 7? Clearly it's not, because I have this function value up here for 5, and then the rest of the graph jumps down to this other branch between 5 and 7. So the function is not continuous. And notice that there's not a point where the slope of the tangent is equal to the slope of the secant on that interval. All right, next one, we're looking at the interval now from 5 to 9. So is the function differentiable between 5 and 9? Yes, it is. Is it continuous? No, it's not. And again, we've got this point at 5 where the function is not actually continuous. However, in this case, there is a tangent line that is parallel to my secant line within the interval from 5 to 9. It's at around, the point of tangency is at around the point where x is equal to 5.7. And then the last one here, notice this time we're really just dealing with the left-hand branch of this function. So we're going from 1 to 5, and the function is differentiable on that interval, and it's also continuous on the closed interval from 1 to 5. Now notice this time we do have a tangent line parallel to the secant line where that point of tangency is between 1 and 5. So all of those, the purpose of that was for you to get a feel for how the mean value theorem works. And what the mean value theorem says is written down here. If a function is differentiable on the open interval a to b and continuous on the closed interval a to b, then there is a number c in the interval a to b such that this is true. Now remember, these are things that we were looking at on the graph. F prime of c is the slope of the tangent line to my function at any point. F of b minus f of a over b minus a, that's my average rate of change or my secant slope. So essentially that's saying that there is a point where the average rate of change is equal to the instantaneous rate of change within that interval. Okay, so notice the results that we have down here where it says which problems are, or for which problems are these things true. So the hypothesis and the conclusion true. So 1, 2, 4, and 7, on all 4 of those, we had the function being continuous on the closed interval and differentiable on the open interval. So the next one says the hypothesis and the conclusion were both not true. So either the function wasn't continuous or not differentiable, and we didn't have the slope of the tangent line equal to the secant line, slope of the secant line. That happened on problems 3 and 5. And then the last one says the conclusion was true, but not the hypothesis. And that happened on number 6, where on this one, we had the function not being continuous, but it happened to be that the slope of the tangent line was equal to the slope of the secant line on that interval. So what the mean value theorem says is that if these 2 criteria are met, then this is guaranteed to be true. It could still turn out to be that way, but the mean value theorem applies when the first 2 criteria that are there are true. Okay, so let's take a look at just the overall idea behind this. A lot of the problems that you're going to do for today are just going to be getting a feel for just the mechanics behind this. Check in the continuity, check in the differentiability, and then using this equation to find the point where the average rate of change is equal to the instantaneous rate of change. We're going to talk about some applications of this in class. So I want to give you an opportunity just to get a feel for how the mechanics work. And then we'll talk about some applications when we have synchronous time. So here's an example of that are the types of problems that you're going to see. It says, given f of x is equal to 2x squared on the interval -1 to 2, is the hypothesis of the mean value theorem satisfied? And the answer in this case, yes, because the function is continuous everywhere, it's differentiable everywhere. So it's definitely differentiable on the open interval -1 to 2, and it's continuous on the closed interval -1 to 2. Okay, so if that's true, find the point C where the slope of the tangent line is equal to the slope of the secant line on the interval between -1 and 2. So what I'm doing here is I'm using the conclusion of the mean value theorem. F prime of C has to equal f of b minus f of a over b minus a. Remember, this is the slope of the tangent line. This is the slope of the secant line. Okay, so I took the derivative. It was 2x squared, so the derivative is 4x. And that at some point has to be equal to the slope of the secant line. So that's what I did here. That's my difference quotient. So that's essentially my function at 2 minus my function at -1 divided by the change in x, which is 2 minus -1. So notice we plugged in c here. because we want to know f prime of c. 4c is equal to essentially 6 over 3, so 4c is equal to 2, and we get the c value to be 1/2. So that's what we were doing with those graphs in the exploration, but now you can actually see how you can calculate those values out. It's not that difficult to do. Now, I did give you a really, really simple example where the derivative was very basic, and the algebra here to solve for the c value was pretty simple. So you'll see when you go through your assignment that some of them are going to be a little more complicated, but it's still the same main idea. Okay, so what I included with this set of notes is a worksheet with some practice AP problems. We're going to talk about these during class next time and get into a little bit more about applications of the mean value theorem, but these are more of the AP style practice questions. So when you go through Math Excel, a lot of times they get very repetitive in the way they ask the questions, and I want you to see some different phrasings and just different presentations of this topic. So that's what these questions are for. So you can work through them on your own if you want, but we will go through those in class next time. And then in addition to that, I also included a practice worksheet that you can do on your own. So this practice worksheet is just more mean value theorem practice. All pretty straightforward, but gives you just, again, a little bit different type of approach to some of the problems in terms of what they're asking you to do and how they're asking you to solve the questions. So number 12 is one that we'll go through in class next time, where they're going into more of an application problem of the mean value theorem. What you'll find when we look at the applications is that most of the time, the answers to these questions are pretty intuitive. It's something that's, if you think through it, you kind of know that it's true. The mean value theorem will give us a way to mathematically justify that what we're intuitively thinking is actually true.